Check, 1, 2, 3.
Yep, we're good.
Got it? Okay.
My name is Nick Moskovitz. I'm an astronomer here at Lowell Observatory. My research interests have always been in relics of the very early era of the solar system, when the planets were just beginning to form. And as the planets were building up and accreting material, some of that material got left behind. And that's what we see today as sort of asteroids and comets and meteorites in the sort of present-day solar system.
For the past year, Dr. Moskovitz has been working on a research project called LOCAMS.
LOCAMS is an acronym that stands for Lowell Observatory Cameras for All-Sky Meteor Surveillance. The basic idea of LOCAMS is to look for meteors, or shooting stars, as they come in through the Earth's atmosphere. By imaging them as they come in through the atmosphere, we can learn things about the origin of these objects and how they're related to other populations in the solar system.
Do you want to try to go up onto the roof? All right.
For each of the LOCAM stations, we have 16 cameras co-mounted on a single board, and each camera is looking at a slightly different part of the sky, so that when we turn the system on, we're essentially creating a mosaic of the night sky, where each camera is looking at a different sort of segment of the sky. The basic technology that we're leveraging is from the security camera industry. Security cameras are very good at capturing all that data and writing it to a computer hard drive. And we have an array of these security cameras that are very sensitive to low light situations, so that's good for our imaging in the night sky. Camera 2 blocked.
Yes, again, device 1.
We're setting up multiple stations so that we can triangulate the position of these meteors. And what that essentially does is creates a 3D image of where the meteor is in space. So we know exactly at what altitude the meteor is at, we know at what angle it's coming in, we know at what speed it's coming in. And so that creates a line in space through the atmosphere. And that line tells us the trajectory of the meteor. So if we project that line backwards in time, that tells us where the meteor came from. And that tells us essentially what orbit it was on before it hit the Earth. For that triangulation to work, the stations have to be a sort of optimal distance apart. And for the meteors we're observing and the capabilities of our cameras and things like that, the sort of optimal distance for us is about 50 miles, 50 to 100 miles. It just so happens that the Discovery Channel telescope is about 45 miles or so away from the Mars Hill campus. It was just sort of a natural decision. It's, there's a spot south of here that just works, here works, so let's go ahead and do those as the two locations. So there's a couple ways to think about the sort of area of the sky that these systems are viewing. Essentially, they're imaging a cone. The actual area that we're looking at in terms of where we're detecting meteors is sort of where that cone intersects with the height in the atmosphere at which meteors are coming in. 100 kilometers from the ground is where a typical meteor is going to start burning up. And so when you project that cone up to 100 kilometers in the atmosphere, that means we're sensitive to a region that goes out maybe 200 miles or so. So it's something about a third the size of Arizona. Meteors come from a variety of sources. Some of them are particles that have been released by comets. Some of them are dust particles released by asteroids, generally formed through collisions. So when two asteroids collide, you produce a shower of fragments. Some of those fragments can make their way to the Earth and pass through the atmosphere as a meteor, and in some cases actually land on the surface as meteorites. There's a whole host of terminology associated with meteor. A meteor is essentially any rock or particle passing through the Earth's atmosphere. If that meteor makes its way to the ground, it survives that passage through the atmosphere and lands on the surface in the form of a rock, then that is when it becomes a meteorite. Our camera system enables the recovery of meteorites that just hours ago or days ago were in space. That'd be a pretty amazing thing. Now again, most of those are really small little particles, pebble-sized things coming in, and they totally vaporize and don't make it to the ground in any way. But the point is that there's a lot of stuff hitting the Earth's atmosphere, a lot of stuff. When you have something that comes in that's a rock that's not centimeter size, but tens of centimeters or meter size, those are the ones that can actually produce meteorites on the ground. They get very, very bright, probably so bright that our cameras might even saturate on them. Yeah, so you get the massive bloom on the cameras. So we would detect something in our images, but we'd have to really go in and process the images carefully, or the video carefully, to be able to say where that thing was coming from and maybe where the meteorites landed.
I really, really hope that we get an opportunity to go out and find fresh meteorites on the ground that have just fallen from space. That would be really exciting.
And even if you do have all the sort of data you need to predict where the meteorite may actually have landed, you then have to deal with terrain that may not be forgiving. There's all these possibilities. So, and then finding a small rock, that can be really tough. So it's not an easy thing to do, but I really, really hope we get the opportunity to do it.